Alright, we're continuing to talk about systems of linear equations. Again, systems are more than one linear equation, so two or more. And solutions of linear equation systems happen at an intersection point. So we're always looking for a coordinate pair or an intersection point between the lines. In this video, I'm going to focus on the different types of solutions that we'll see algebraically. So if we graph them, you can easily see two parallel lines and how they don't intersect. But what does that look like algebraically? That's the type of stuff we're going to be talking about. So let's just get going in this example here. One of the big tricks in solving systems is not to do more work than is necessary. So if I just attacked this problem without even thinking about it, I would probably end up doing more work than I needed to. There's two different ways we can think about this problem right here. One is we could solve it by substitution, because this coefficient is 1, so we could solve for x and then substitute that into this one. We could do the combination method. All we would have to do is multiply this equation by -2. But both of those are kind of more work than what we need to do. If we actually just solve these equations for y, so put them in slope-intercept form, y equals mx plus b, let's see what happens. I'm going to take this first one, and I'm going to subtract x from both sides, so -x plus 3. And then I'm going to divide by -2. So we get y is 1/2, positive 1/2 x, minus 3/2. Okay, so let's hold on to this. Oops. I want to keep this in my back pocket and do the same thing to the bottom equation here. Let's solve it for y. So if I subtract 2x from both sides, I get that, and then if I divide by -4, then I get, again, positive 1/2 x minus 7/4. And if we just take a look at these two equations, then we don't have to really do any more work if we know how they relate. Take a look at our slope here, the number right in front of that x. It's the exact same in both these equations. If you remember that linear equations, or lines that have the same slope, are parallel lines. And if you can recognize that, you definitely have to do far less work. So these are parallel lines, they never intersect, so there is no solution. There's no solution to this system because they never intersect. Now we could have done it the other way, and I'm going to show you what that looked like. So let's try and erase all this stuff here. Oops, we need a white. Let's get rid of all this stuff, go back to the beginning. So let's say we didn't look at those equations, we didn't see how maybe they had the same slope, and we decided to, I would say, solve it by substituting. That's probably the next easiest one. So let's do that. Let's solve it for x, this first equation. So x, go back to my original stroke here. Dang it. Ignore that. Solving for x here. So if I add 2y to this top equation to both sides, then I get x equals positive 2y on the other side plus 3. Alright, let's save that and let's substitute it into this equation right here. So now we have 2 times 2y plus 3 instead of x, minus 4y equals 7. Distribute, so 2 times 2y is 4y, 2 times positive 3 is positive 6, And keep solving for y now. Combine our like terms here. We got a positive 4 and a negative 4. So anytime we combine opposites, we always get 0, right? So those go away, and all we're left with is 6, this positive 6, and on the other side we're left with negative 7. Well, this seems like a weird statement here. Is 6 equal to negative 7? No. So, no solution. That's what happens when you have a system of parallel lines and you're trying to solve it algebraically. You end up with an untrue statement, or you end up with something on the left side that's not equal to the right side. And it comes in all kinds of varieties, but basically you end up with an untrue statement. This is not equal to that. And when that happens, you have no solution, and you should think, oh, we got parallel lines here, because there's no solution. There's no intersection between those two lines. Alright, so hopefully it's starting to come together here. Let's get rid of this, do a new example. So that was an example of no solution, right? We always have 3 different ones here. We have infinite amount of solutions, right? If we get the same line. Let's see if we can do an example of that. Alright, so if we look at these two equations, hopefully you can see that well, solving for y to compare their slopes would be a bit of a pain, so I'm not going to do that. Trying to solve it by substituting would be pretty challenging, so I'm not going to do that either. So I'm going to try the combo method. I'm going to try and combine these two equations, but I got to get one of my x's or my y's to cancel here. And I can't do that by simply multiplying one of these equations by a number. So in this example, I have to end up multiplying each of these equations in order to get one of my x's or my y's to cancel here. So what would be easier? Let's see. Common multiples of 6 and 15. The first one we get to is 30, right? So I'd have to multiply this top equation by 5 to get 30x. Yeah, I think that's slightly easier. Well, yeah, it's about the same, because the common multiple between these two would be 50, so we'd have to multiply that top by 5 anyway, so let's just go ahead and multiply the top equation by 5. And so then we would get 30x, 5 times 6x, and then 5 times negative 10y is negative 50y, and 5 times 12 is 60. So now we got to multiply this bottom equation to get negative 30. Well, we multiply it by 2, right? So there's negative 30x, then 2 times 25 is positive 50y, and 2 times negative 30 is negative 60. And here's where we start to see what happens if we get the same line. Our x's cancel, right? Those are opposites, so we get 0 x's. Our y's also cancel, so we get 0 y's, so we basically have 0 on the left side. And on the right side, look at what happens. 60 combined with a negative 60 again gives us a 0. So now we have a statement, 0 equals 0. Is that a true statement? Yes. So in that case, when we have a true statement, we have an infinite amount of solutions, because these end up being the same exact line. So the same line would intersect itself over and over an infinite amount of times, right? So that's how we get an infinite amount of solutions. You could also shorthand it using our symbol, infinite solutions. Alright, so that's what an infinite amount of solutions looks like algebraically. Again, if we were to graph this, we would end up graphing the same exact line. So anytime we get a true statement where the left side equals the right side, then we have an infinite amount of solutions. Okay? And that is in contrast to what we just did, where we had a false statement, and that was a set of parallel lines and no solution. So I think that's a pretty good example of systems. Again, just real quick review. We could have one solution or one intersection point, right? One intersection. And that's given in a coordinate pair. We got an xy value when that happens, right? So there's one possible solution for a system. The other is that we have an infinite amount of solutions. Infinite amount of solutions, that's where if we were to graph it, we would graph the same line. And the third and last possible solution we could ever have is if we have parallel lines and we have no solution. So no solution, and that's caused because parallel lines never intersect, so we never have a solution to the system. All right, good luck with systems.